All right, guys, here is 2016 number 6. Here is a pretty good one. This is probably going to be on your AP test because it is dealing with series in general. All right, so let's look at this. The function f has a Taylor series about x equals 1. That means it is Taylor, not Maclaurin. Remember, if it's Maclaurin, it's about x equals 0. This is about x equals 1. That converges to f of x for all of x in the interval of convergence. It is known, and these are key things, f of 1 equals 1, the derivative at 1 equals negative a half, and the nth derivative at x equals 1 is given by here. So all the other derivatives is right there for n greater than or equal to 2, so the second one. So part A, write the first 4 non-zero terms in the general term for the series for x about x equals 1. So Taylor's series. Remember what I told you guys. You guys should remember this. And now that you guys can pretty much use your notes on this test, right? You should have this written down somewhere easily. That the Taylor series is f of a plus the first derivative at a times x minus a plus the second derivative at a over 2 factorial times x minus a squared plus dot dot dot. Got it? That should now be written down somewhere. So now you guys have to plug it in. What is A? A is 1. So in our case here, what is f of 1 going to be? So here's our f of x equals. So f of 1, if A is 1, well, they told us to us. F of 1 is 1 plus the first derivative at 1. Again, they told it to us. It was negative a half. So negative a half times x minus a again is 1. Plus, now to get the second derivative, you've got to use this formula right here for all the other derivatives. Got it? So in our case here, n is 2. So negative 1 squared is positive 1. 2 minus 1 is 1. 1 factorial is just, 1. So it's going to be 1 over 2 squared is 4. I'm just going to keep writing it as 2 squared. I think that's going to work out well. Over 2 factorial, well, that's already in the denominator, so I'm going to put 2 factorial here, and then it's x minus 1 squared. So now, let's go back. The first 4 non-zero terms, so it's 1, 2, 3, I need the fourth one. So, plus, now I'm at 3. Negative 1 cubed is negative 1, so I'm going to have a negative. 3 minus 1 is going to be, it's 2 factorial, which is just 2, right? Over 2 cubed, and then it's the third one, so I'm doing 3 factorial times x minus 1 cubed, dot, dot, dot. All right, I'm going to simplify this. So I've got f of x equals, this first one is 1 minus a half times x minus 1 plus, I can't really simplify this, I'm just going to keep it going. It's 1 over 2 squared times 2 factorial times x minus 1 squared plus, which let's be, hold on a second. I'm actually going to get rid of this 2 factorial because 2 factorial is just 2. Okay, minus 3 factorial is 6. 2 goes into 6 here, or you just get 3 times. So that's going to be minus 1 over 2 cubed times 3 times x minus 1 cubed plus dot, dot, dot. So now let's do our general term. Well, look, it's an alternating series. I want positive, negative, positive, negative. So I know I'm going to have a negative 1 to the n. Over. Here I've got 2, 2 squared, 2 cubed. So that's going to be 2 to the n. Here, what's multiplying by the 2 in the first part here is just a times 1. This is a times 2, a times 3, so that's times n times x minus 1 to the nth. And there you go. This is a 4-point problem out of 9 because you had 1 point for the first 2 terms, 1 point for the third term, 1 point for the fourth term. So here's the deal. You get 1 point because they gave you these two things. Because you had to use this formula for the third and fourth term, you got a point each. And then a point for the general term for figuring it out. So even if you couldn't figure out the general term, but you got everything else, that's 3 points. It's really, really good. So moving on from there. Part B. Let's see. Part B. The Taylor series for f about x equals 1 has a radius of convergence of 2. Find the interval of convergence and show the work that leads to your answer. Okay. Well, way you can realize it, multiple ways to realize. You could do the ratio test is actually what this is asking you to do, is the ratio test. Kind of. So what happens is if you do the ratio test, I'm trying to figure out the best way how to explain it. If you do the ratio test, you know you're going to go from, whatever it is going from -1 to 1. Correct? But now, nope, you know what? Never mind. That makes no sense. We're going to have to do the ratio test. Sorry, guys. I was trying to avoid it. So ratio test, remember, is the limit as n approaches infinity of the absolute value of a sub n plus 1. So all the n plus 1s. So -1 to the n plus 1, that's going to be positive. But you're going to have the absolute value of x minus 1 to the n plus 1 over 2 to the n plus 1 times n plus 1. Right? So all those have n plus 1s. Times the reciprocal of the original, which was 2 to the nth times n over x minus 1 to the nth. Where did I get the original? Guys, this is from part A. This is what we got in part A. So now, let's simplify. Let's see. This is going to cancel out with one of those. This is going to cancel out with one of those. So you're really going to have the limit as n approaches infinity of x minus 1 over 2 times n over n plus 1. Now, remember, it's the limit as n approaches infinity, so I'm looking at this part right here. Well, this is infinity over infinity. You can look at the powers. They're the same, so the coefficient is just 1. So all you get is the absolute value of x minus 1 over 2. Now, according to the ratio test, when does this converge? It converges when it's less than 1. So that means from -1 less than x minus 1 over 2 less than 1. Got it? Solve for x. Interval of convergence means you got to get the x by itself. So here you're going to have -2 less than x minus 1 less than 2, which you could have started right here because you knew it was x minus 1 and the radius of convergence was 2. So you could have just had x minus 1 going from -2 to 2. That's the shortcut we could have used, but I wanted us to get here. So I'll add 1 to everything to get rid of that plus 1, sorry. So then you get -1 is less than x less than 3. So that is our interval of convergence. But with interval of convergence, you've got to plug in the endpoints and see if it converges at those points. Got it? So if you plug in -1 in for x from part A, so you would have, well, the first part, if I plug in x equals -1, then you'd have 1 is the first number no matter what. But then you'd have 1 minus 1, sorry, -1 minus 1 is -2 times the -1/2 would be a +1. Plug in -1 in the second one, that's -1 minus 1 again is -2, but -2 squared is +1. and you got 1 squared, you'd get plus 1 plus 1 plus a half. What happens is this is a harmonic series, really. So this diverges. So it would not converge with negative 1. If you plug in x equals 3, again, you're plugging it into the series from part A, the one that we created. The first number is still 1. If I plug in 3, 3 minus 1 is 2. 2 over 2 cancels out. That becomes negative 1. Plug in 3 here. 3 minus 1 is 2. 2 over 2 cancels. You get 1/4. Yeah. I think 3 minus 1 is 2. 2 squared is 4. Those cancel. That becomes a half. Plus a half. Then you'll get minus a third, plus a fourth. This is an alternating harmonic series, which converges. So it converges at 3, so that 3 has to be or equal to, so your interval of convergence is there. So you get 2 points for that. But if you get 1 point, if you just go from negative 1 to 3, you'll get a point, and that's good. That's fine. All right. Part C. The Taylor series for f about x equals 1 can be used to represent f of 1.2 as an alternating series. Use the first 3 non-zero terms of the alternating series to approximate f of 1.2. So go back to A. Got it? Go back to part A, and it says use what? The first 3 terms. Well, part A, our first 3 terms was what? 1 minus a half times x minus 1 plus 1 over 2 squared times 2 times x minus 1 squared. Those are the first 3 terms, not the third degree. Third degree means it has to be x to the third, right? This is technically a second degree, but it's the first 3 terms. Now, what am I going to do with these first 3 terms? It's telling us is to plug in f of 1.2. So we're going to say, okay, f of 1.2 is approximately, and I'm going to plug in 1.2. So that first term is 1 minus a half times 1.2 minus 1 is 0.2 plus, this is 2 squared is 4 times 2 is an eighth. So an eighth times, again, 1.2 minus 1 is 0.2 squared. So when I put this all together, that's going to be 1 minus 0.1 plus 0.005. Yeah, because think 2 over 8 is 1 over 4 is a half, but it's point that, so yeah, so it goes over. You add these together, you get 0.905. And there you go. So very straightforward here for part C. Just 1 point. Letter D. Show the approximation found in part C is within 0.001 of the exact value of f of 1.2. What does this mean? This is just a Lagrange error bound. It's just them doing the error or the remainder, where the remainder is your function at 1.2 minus your series at 1.2. And remember, we went to 2, the second degree, because it was a 3 terms, right? So that means your n was 2, our a is 1, the x is 1.2. But really, they're just asking you guys to use the next term. You have the next term from part A. In part A, the next term is the third degree, which was 1 over 2 cubed times 3 times x minus 1 to the third. Well, what was x? Is 1.2 minus 1 to the third. You're just plugging in 1.2 into the very next term. So what happens is this over here becomes 2 cubed is 8. 8 times 3 is 24. So you get 1 over 24. times 1.2 minus 1 is 0.2. 0.2 to the third is 0. Will be 0.008 because it's 0.2 however many times. So if I wanted to move this decimal to the right 1, 2, 3 spots, that means I have to move this decimal here to the right 1, 2, 3 spots. So this is really 8 over 24,000. Divide this out. This is really 1 over 3,000 because 8 goes into 24 3 times. 1 over 3,000 is less than 0.001. So that's the big thing you guys have to remember about the Lagrange error bound, or the remainder estimation theorem, is that it's just the next one